Hey QED coders, this is Michael. Last week we talked about spanning trees, and we talked about a bug in Janaga.net that I want to fix for you today. Ordinarily, you can join me at immutablearchitecture.com on Discord. Today we're doing this one offline, but usually you can join me there. And so the first thing that I would like to do, I would like to clarify, or I should say correct, some terms that I used. The most important term that I used was the one that I used in the title. I called this a spanning tree. That is incorrect. The most important thing in mathematics is getting things by their right names, and spanning tree is not correct. So the idea behind what we're trying to do is we've got a graph. So we looked at this fact type graph, and this is a directed graph. I'll also go into a little bit of detail why I didn't just say directed acyclic graph. So this is a directed graph, and then we want to look at it using its undirected graph projection, which is basically taking all the arrows off. And then what I said was we find a spanning tree. That part is incorrect, and let me tell you why. If we go back to the issue that we're trying to solve, you can see that a specification creates different paths within this this graph. And if the specification is minimal, so that means it's connected and it has no additional path constraints. It has nothing extra besides what it takes to make it connected. Then what you get is a spanning tree. But there's nothing in here that says that you can't have additional paths. In fact, that is very much allowed. If we go back to the code, let me pull up the code right here. And here we are generating some SQL. You will see that when we go through our different conditions, we've got the predecessor has already been written, and the successor has already been written. If this has happened, if both the predecessor and the successor are already in the traversal of the graph, then we don't add another join clause. We don't bring in another fact alias. We simply add to the where clause an extra condition on a on a couple of facts that are already in the query. So that's important. Because this is possible, that means that the thing that we produce might have two edges, or two paths, I should say, between two different facts. We might add an edge between two facts that are already connected. If they're already both part of the graph, and we built this graph by building connections, then those two facts are already connected. And so this becomes a redundant edge, or an extra constraint. Now, while that's important for how the graph actually functions, that means that it is possible for you to create a specification that is not a tree. And a spanning tree must be a tree. A tree has no cycles. It has just enough edges in order to keep it connected. So, what we're trying to find is not actually a spanning tree. So this name is incorrect. What we are actually trying to find is a graph traversal. And so specifically, we are trying to traverse the graph in such a way that it is connected. It's just one single traversal. So there's a set of names in the nomenclature, in the literature about these graph traversals, and the names at first seem to make sense, but then as you get into them, they really don't make much sense. So the name that we want to give to the graph before we've traversed it is a forest. So it's some collection of trees. And then as we're traversing and we bring things together, bring the nodes together, what we will do is we will create a tree. That's a minimum set of edges that fully connect some set of nodes. And then we can add another node to the tree. So as you are traversing, you reduce the size of the forest, the number of trees in the forest. So before we've added any edges, this particular graph has 4 trees. Each one of these nodes is its own separate tree. And then as we do the traversal, we add edges, and we add edges such that we reduce the number of trees. If we can get all the way down to 1, we have a complete graph, and we have found a spanning tree within that graph. And we stop. That's the thing. In this algorithm, if we have extra connections, if we want to traverse an edge twice, or maybe visit some node but then find our way back to the graph some other way, then we won't create a tree. We will create something that has redundant edges, aka cycles. Okay, but is any of that getting us closer to the solution to our problem? Let me remind you what our problem is. I'll go all the way back to the tests, and you will see that when I run this test, I get an exception. It tells me that I will let it do its thing, but in the meantime, I will also take you to... Oh, wait a minute. I'm looking at the wrong thing. There it is. Test Explorer. Okay. All right. So it tells me that neither predecessor nor successor fact has been written, and it gets us down here, where we've already ruled out that both the predecessor and successor have been written, and therefore we write a redundant edge, aka not a tree, or just the predecessor but not the successor has been written, so therefore write out the successor fact, or just the successor but not the predecessor, therefore write out just the predecessor fact. So those are the various conditions. We've ruled them out, therefore neither predecessor nor successor has been written. And we don't know how to create that join. So that's the problem. What's the solution? Last week, I proposed a possible solution. That solution is that when we build the... it's going to be result description builder. Yeah. Okay, there we go. So when we build, go all the way back up. We don't need this there anymore. We'll go all the way back up here, and we're adding a path condition to our result description. We first, don't worry about that condition right now. We first go through the right-hand side, and we walk up the roles. And that follows all of the predecessor relationships from the existing fact, some prior label, up those various predecessor roles. And then, once we've gone up the right-hand side, we walk up the left-hand side, which starts at the unknown. So we're starting at, flipping back over here and looking at the graph, or the specification, we're starting on the left-hand side at saved, that's the unknown, and the right-hand side at the prior label, in this case, a given. So, walking up from the left-hand side, we follow a bunch of predecessor steps from there, and we should end up in the same place. They should join in some common ancestor. And now, in order to get from the prior label to the new unknown, we have to reverse the right-hand side. And so that helps us to walk up to the common ancestor and then back down. And so that's what this algorithm is doing, and it's adding edges to this graph as it's building it. So my original recommendation here was, let's take a look at the second one and notice that we have already completed a path from some prior label, which is already in the graph, to the unknown. So now the unknown is in the graph. So we can walk the other paths forward from there, and we know that we won't get into any trouble. Is that sufficient to know that we are always starting from someplace in the graph? And I say no, it is not. Because it would be possible for the very next unknown to start with a path condition that joins not the given that we started with here, but brings in the other given. So if we start down a path from school, then we are joining all of our nodes, all of our labels to school. If we don't have any references to saved, then we have created a different component of the graph, a different connected component of the graph. And the goal here is to make sure that we have a connected graph. I won't say completely connected graph, but completely means something different, so I won't say that. We've got a connected graph, which means we can't bring in another given until we can approach it from the correct side. So here we have session joined to saved, and now we can approach school from the other side. And that's the point at which you will introduce your second path for the same unknown. Okay, so saying all that, that means that there are situations in which the fix of walking the second one backwards isn't sufficient. So if we were to join to school before this, and then here saved joined to that school. Like, for example, if I took details and I joined details to school, so I just had this, this little part right here. I just joined details to school first, and then I introduced this. Then we would end up in a place that that the solution would not fix. You know what? In fact, that is a really good test. Let's do that while we're here. Okay, so I am going to switch to Visual Studio Code because it does a much better job with GitHub Copilot. And I know that GitHub Copilot will be able to help me here. So, loading up the Janaga.net Visual Studio Code. Okay, so let's go to this test here, which is in Query Generator Tests. So, Control P, Query Generator Tests. And let's go down to that test there. Perfect. Okay. So I should be able to handle a specification with two paths. That's what this one is. But I should also be able to handle a specification that is split with two paths. So let's do that. So we've got effect, public. We are able to do this just synchronously. Should handle specification. We'll call this a split specification. Okay, and of course it has no idea what I mean by that. But what I mean is that I'm going to take this And I'm going to first introduce details. So let's do facts of type. What is the type of details? Order details. Okay, so now it helps me out. And it says word details, detail school equals school. That's perfect. Then I don't want to then go on to detailed orders. I want to join this. Now I could switch all of this to the keyword syntax, and it would be easier to see. Since I've got this opportunity, let me show you what it would look like if we were to do it this way. Select many. Now we can bring in facts of type saved order and join those. So that is how you do that with the extensions. With keywords, it's just from where and then from where. So it implicitly does a select many. Now, the important thing here is that I have traversed from school to details, and then on the very next thing, I want to flip this around to make it more challenging. I traverse from session to saved. So when I write the specification out like this, I am forcing it to approach from two different directions and take different steps before it ever finds, here at the very end, the way to connect those two components, those two subgraphs. So details comes from this connection, which is connected to school, and we connect that to saved at the very end. Meanwhile, session is the other given. So approach them from two different directions. The solution that I came up with of reversing the path condition, the second path condition, won't help here. This path only has one edge in it anyway, so the reverse is still that edge in that direction. So let's let Copilot come up with the rest of the test for us. It's going to take a guess at what it thinks the sequel should look like. And it gets the right shape. It might not be the right sequel, but it's the right shape, and we can evaluate that later. But you can see that it's trying to do saved session and then saved details and then details school. So at least it knows the constraints on SQL, that you have to walk the graph, you have to traverse the graph in a way that keeps it connected. Unless you're going to do from A, comma, B, and then put the connection in the where clause. But we don't want to do that, as we discussed last week. So, now that that's all generated, we can come back to Visual Studio and get a better testing experience, I think. So, built. And now we should have two things that fail. Let's run that. And so we see here's a, oh, that's interesting. It's able to come up with, a specification. That's really interesting. I did not expect that. Okay, we're going to have to look a little bit more closely at that and see why it worked. I thought that was going to fail, but fail in a way that we would not be able to recover just by reversing the order of paths. In the meantime, what I'm going to do is fix this generated SQL, and we'll get Copilot Chat to help me out with that. Please, always say please, update this test. You know what? It's got dictation built into it. It'll probably talk back to me. I don't know. Well, let's try this. I won't be able to paste if I dictate. Anyway, getting distracted. Please update this test to match the actual result. Paste. And now it can see what the actual result was, and it can see what the test is doing. It's failing because the SQL does not match the actual result query. Good. You got that far. And the differences are in the order of the fields in the select clause and the join conditions. Oh, okay, good. Also, the actual query has an order by clause. Oh, I forgot that part. So here is the corrected code. So I just insert at cursor, boom, and we've got the corrected code. Now that we've got that, let's read through it. Flip back here. Okay. Okay, so we're going to start at the session. Then we go to F4, the school, and then F2, and then F3. Interesting. Okay, so starting at the session, we go saved session. So we're going down to a successor. That's saved. And then we go saved up to predecessor details. So saved is the saved up to predecessor, or up to successor, up to predecessor details. So yeah, that's not the correct order if it was actually that. Let's see what it's really doing. Let's take a look again at our labels and see what it's really doing. Okay, we assume that it is starting with session, and it labeled it F1, or it gave it the alias F1. And then we go down to the saved fact F2 with E1. So far, that is consistent. Now, I don't have any guarantee that that's actually F1 is session and F2 is saved order, but so far, that's consistent. And then we go saved to details, bringing in F3 details, saved to details, F3 details. And it's saying here that E2, the F2 is the predecessor, which if this were saved order and details, that would not be the case. F2 would be the successor. So I think it just got these labels wrong. What it's actually doing is starting from school. So from school, it is going down to details. So that's details. Details. And this is details school. Boom. And then from there, it's going down again to saved order. Saved. And so that's, that is saved details. So that one is, it did get that one correct. Accidentally. And then from here, we're flipping the direction. So from saved, we are going back up to session. And we're following session saved. Nope, saved session, sorry. Saved session. Okay, so starting at school, school being the predecessor, we come back, we come down to details. Now details again is the predecessor, and we come down to saved. So we, boom, predecessor to details, details, predecessor to saved. Good. And now from saved, we go the opposite direction. So now F3 saved is the successor, and F4 session is the predecessor. Okay. So yeah, these aliases are now incorrect for this one, but that is what it generated. And that is a correct traversal. Let's go ahead and also update these. We had school was F1, F4 was session, session, and then F2 was details, and F3 was saved. Okay. So now, surprisingly, with that, this test will pass. Boom, boom, green, that test passes. Okay. So, that was interesting. I didn't expect that one to pass, but we got ourselves another test. More tests are good anyway. Excuse me. So, I should be able to find other scenarios in which I can create failures. So, even though I haven't found that scenario, I do know that that scenario exists. I cannot prove that reversing this path will always fix the issue. So, what will always fix the issue? For that, let's go on back to our SQL generator right here. The issue really just comes down to the fact that we are walking these edges in the order in which they are given to us. Why are we doing that? There's really no reason that we should walk these edges in the order in which they're given to us. So that now we can generate these edges however we want to, and then we walk them in the order in which we want to walk them. Here's another interesting thing about graph theory. A graph is a set. It's a set of nodes and edges. You can consider it two sets, a set of nodes and a set of edges. I've seen it described in both ways. Each one is fine. So the idea of traversing a graph is not, you don't have to think about it as placing yourself on a map, finding a bridge, and then walking over that bridge. And now you're in a different place on the map. Find another bridge, walk over that bridge. So if you were to place yourself on a map, you could say, you could explore this graph. You could say, start here, follow this edge, follow this edge, follow this edge, and you'd find your way to the other place. But another way that you can think of it is, I just have a set. I just have a collection. Let's talk about the set of edges. I've got this set of these three edges. And being a set, it's not ordered. So I just can reach into that set and take a look. Oh, that edge is in there, that edge is in there. So looking at it from that direction, I can pull these edges out of the bag in any order that I want to. How about I pull them out in such a way that we can hit this condition, we can hit this condition, we can hit this condition, but we cannot hit this condition. How about we just do it that way? What would that produce? That would produce a traversal of this set of edges. Just one possible traversal. We don't have to have a shortest traversal. We don't have to have a traversal with minimum weights. We don't have to have a traversal that is a tree. We can just find any traversal. And because all of these edges are important, every edge here represents a constraint on our graph. We want to make sure that we include every edge. So let's just take these edges in the order that keeps us on a good track. So let's take the edges in the order that either the predecessor or the successor is in the written fact indexes. That seems nice and simple. That way, if we take this edge first, and then the very next edge that we see is that one over there, then we'll say, hey, wait a minute. These two have not yet been written. I'm not going to take that one yet. Let's take this one instead. Okay, now the graph contains these three nodes. And then I go back to my bag and I say, okay, that edge is in there. I can take it now. Well, let's process that. And you'll end up with a nice connected traversal. You won't be jumping over any nodes. Simple algorithm. And yeah, doesn't mess up any of the existing code. So let's go back to Copilot, because Copilot is really good at this kind of stuff. And I want to look at SQL generator. So SQL generator. And I am down here on line 120. Get me to the same place. There we go. Let's go ahead and put chat away. I do actually prefer chat, but for this, we can do things with inline generation. Okay, so instead of just walking edge to edge, what I want to do is keep a list of the remaining edges. So let's do it this way. Our remaining edges, we'll set that equal to this list of edges. Now this is an immutable list, so that means I don't have to copy it. I can just say it's the same list. Because as I remove things from remaining edges, I'm not going to do that by mutating the list. Therefore, this is going to stay exactly as it is. So, yay, immutability. Now, instead of for each over the edges, I'm going to say while the remaining edges dot any. So I have remaining edges. Okay. Now it's probably going to try to come up with a complete algorithm here, and it's going to get it wrong. So it's saying, hey, let's see if we just take the first edge and then do these things. No, not what I'm after. I don't just want the first one. I want the first one that matches a particular condition. That condition being that either the predecessor or the successor has been written. So I will say var edge index is equal to remaining edges dot find index. And now we've got a really good guess. So I want to find the index of the edge such that either the written fact index contains the predecessor or the written fact index contains the successor. There we go. All right. You know what? Let's explain to people why this is true. Comment, find the first edge that has a predecessor or successor fact that has been written. That is a very specific description of what this code does. Why do I want to do that? Maybe it's because I want to find the first edge that is connected to the rest to the first edge, rest of the graph. Let's just do it. Let's say it that way. Now that tells us why we're trying to do this. Okay, so we've got that edge index. Now from there, the rest I think it can figure out. So if no such eggs exists, then we have a disconnected graph. Ha-ha! We'll let it do its thing. Boom. Disconnected graph. Let's be friendlier than that, please. Okay. The specification, because that's where this graph came from, is not connected. Okay. Maybe somebody getting that error would understand what that means. I'm not entirely certain of that yet. So we will do a little bit of education within the error message and on the website. But for now, that's good. Okay, so we have an edge that's connected either to the predecessor or the successor. Now what do we do? We add the edge to the joins. Yeah, that's good. And how do we do that? Exactly all of this. Oh, wait a minute. We need to first get the edge. There we go. And now that we've got the edge, we can remove it from the remaining edges. And now we can continue all of this stuff. So in fact, move that comment down. There we go. Okay. So now this reorders the edges as it's walking them, such that it still only visits every edge once. It keeps going until it visits them all, and every time it pulls an edge, it's going to match this condition, because this would be predecessor and successor, so the OR would still match. This condition being just predecessor, so that would match. Or this condition being just successor, so that would match. It will never actually fall into this line of code. So, I have proven to myself that this will never happen, but there's no way that I can prove to the compiler that this would never happen. Yeah, it seems like maybe, but that would require something like oh goodness, what was that tool that I used to teach? So it did design by contract in .NET. Anyway, Bertrand Meyer stuff. It was really cool, but ultimately compile times were really long. So you could teach this thing that this is a precondition, and therefore by the time you got into this code, you would know that either this precondition or this precondition. So this union of those two is true. So therefore, this will never get hit. And immutability helps in that regard, but we're not using that tool. Code contracts, that's it. Anyway, so now we can probably tell it that by the selection of the edge, we know that one of the facts is already written, therefore we should never reach this point. Good. Okay, yeah, Copilot, yeah, it can figure out what I am about to say. It can figure out, okay, this is the area that you're in, but it does that just by pattern matching. And sometimes what this looks like matches a different pattern, like calling a subgraph a spanning tree. It matches a certain pattern, but no, it's not correct. All right. So now we've got this. Let's go back to here. Here's our new code. And let's go back to our test explorer. And let's just run all those tests. Let's see, did this fix the problem? Let's see. All right, it fixed the original problem, but now it came up with a different set of SQL. I am curious about this now. So, to satisfy my curiosity, what I'm going to do is I'm going to commit these changes. I'm going to say, take the edges in an order that keeps the graph connected. Commit that. Now that I've got an error message that tells me why this fails now, I'm curious how it came to be. Oh, yeah. For chat, I want to go back to Visual Studio Code. Okay, back to here. And we are talking about not two paths. Wait, a split specification, yeah. We are talking about split. No, we're not talking about split specification. What? Oh, okay. I see what happened. All right. So, our new test, the split specification, that continued to pass because it produced the same SQL both before and after. That's an important point. Let's get back to that. But this one failed, but now for a different reason. It failed because the SQL is incorrect. Here, I just took a guess what did I get wrong about my guess? So let's come back up here, handle a specification with two paths. Let's ask it, please fix this assertion as well. Paste. Why is it failing? The order of the fields in the select clause and the join clauses. Also the order by clause. All right, yeah, I forgot about that one. So let's paste that in. Flip back. We can see that it updated the order. And let's just to make sure, run this. We'll watch this turn green. It turned green. Okay, and now that I did the git changes, I can see specifically what was it that I got wrong. Okay, so it ended up in a different order. So we had F1, F3, F2 instead of F1, F2, F4. Okay, so that session details saved is what it thinks those mean. We'll double check those aliases. And actually, those are labels. These are labels. These are aliases. Mapping of alias to label is what we're double checking. So, okay, this is kind of an interesting thing right here. You can see that we had E1 to F2, and then we jumped to E3, F4. So we jumped from edge 1 to edge 3, skipping over edge 2. It brought edge 2 in later. And that makes a lot of sense. So here, remember, we're starting with the same edges with the aliases that they were given by the thing that walks all the paths. So that E1, E2, and E3 is this E1, E2, E3. So those line up. So we went from E1 straight to E3. E1 straight to E3. Okay, maybe they don't line up. Interesting. Yeah, so from let's just double check the mapping before we get any further into this. So if we start at session, and session is the predecessor, then we will end up at, yeah, so it's already got this wrong here, because here it says that session is the, well, sorry, session is the predecessor. Saved is pointing up to session. So does that line up? Session, saved, session is the predecessor. Good. Now F2, we have F2 being the successor, where F4 is the predecessor. Boom, boom. So that should be details, not school. That's the thing. So saved doesn't even go to school. Saved goes to details. Details. And then here, this is backwards. It's not school pointing to details. It's details pointing to school. Details, school. And now that brings us finally to school. So F3, we believe, is school. Yeah, details is not even in the tuple because it's only the labeled facts in the tuple. These are the three labels, no label on details. All right, so session is F1, F3 is school, and F2 is saved. Okay, so now that is the correct mapping of aliases to labels. We can also double check the where clause here. The where clause should only reference givens. So F1, session, and F4, school. So we're talking about F1 and F3. Oh, wait a minute. Yeah, these are So that became F3. That became F4. Yep. And then details to school. That was edge 2. And that was edge 3. Edge 3 was saved to details. And edge 1 was still saved to session. Saved to session was still edge 1. Okay. All right. Now we've got this correct. We've got this correct. So the givens are F1 and F3. F1 and F3. Perfect. Okay. Now we understand this SQL. Now let's take a look at the difference. So part of the difference is how we've assigned the aliases, which I didn't expect that to change. I thought the alias assignment happened. Well, this was just my guess. So my guess was just wrong about how it was going to assign the aliases. Okay, we're fine with that. So we go from E1 to E3, followed by E2. So we go E1 to E3, followed by E2. And so it's actually easier to look at it this way. The difference is just, I got it wrong. So E1 to E3, followed by E2. So we held off on E2 until we brought in E3. E3 says, okay, I'm connected. My successor has already been written. My predecessor hasn't. So let me go ahead and add that predecessor. And now let's look back again at this list of edges. I have E2 that joins to details. So I can continue the graph from there. And then if at any time it ends up with, where did we go? Here. Nope, not there. Yeah, here. Existential where clause. We're not. I'm going to have to double check this one and make sure that this exception, yeah. Maybe. No. Okay, I'll go back and double check that one. Okay, I got lost for a second. Here we are. This is the code that we modified. So, yeah, we can't find our way here anymore because we are pulling them in this order. Okay, this is what I was about to say. If at any point we find that we can't pull any edge because neither the predecessor nor successor has been written, and we make it all the way through the remaining edges, none of them meet that condition, then that means that's part of another component of the graph. There's no connection between these two graphs. Something is referring to another given that we didn't bring in to our graph, and therefore the specification is not connected. So one of the things that I would like to do is to find that condition earlier before we're trying to generate SQL, because that's never a correct specification. And then another thing that I would like to do is to prove to myself that that situation never occurs when you're computing an inverse, because you compute inverses automatically, and can it produce a specification that it then cannot produce SQL for? Really good questions. Some really good math that I want to get into. But this gets us one step closer to having a working solution for my team. Now, there's one last thing that I do want to analyze before I say, yes, this is the correct solution. And that is there any possibility that this made things worse? It's always a bit of analysis that I go through once I've finished up a complicated change like this. So, is there ever any way that we would get to this exception where the previous code, before I made this change, would not have gotten to this exception? And the answer is no, there is no way that that would happen. Why is that? Well, before, it was traversing these edges in the order in which they were given. If the order in which they were given always makes it here, here, or here, but never here, then that means that the order in which it was given always had either the predecessor or the successor in the written fact indexes in that order, which means that it would have found the very next edge, because find index finds the edges in the very next one that matches this condition. So it would have found the very next edge in that set of remaining edges. So it would continue to walk them in exactly the same order. This code doesn't change the behavior of the system for anything that didn't throw an exception before. So the only thing that this code does is prevents exceptions. It can't cause new ones. So that makes me happy. Also, the fact that it now passes all the tests, that makes me happy too. Let's go ahead and run these tests too, even though these tests don't touch this code that I just changed, but I do want to see them run. Yeah, they all run. Perfect. So that means we're good. That means we can check this in and create a new version of Janaga.net. All right. So that is how we can fix the exception doing a graph traversal. Let's meet again next week when we'll again be able to talk to Jan, and we'll continue down the path of creating a working Janaga.net application. So until then, build something awesome. See ya.